Okay, today we are starting with the particle kinematics. So, in the Newtonian mechanics, as we know, the time acts as an independent parameter. Actually, in the backdrop of time, all the events take place. Okay. While in the relativistic mechanics, the time is not an independent parameter, it gets mixed up with the other 3 dimensions. So, as a whole, here the time universally in the Newtonian mechanics as a whole, time universally applies to all the events. Okay. One single time will apply to all the events, while in relativistic mechanics the same thing is not true. Okay. So, therefore, while describing the coordinates of any particle in a reference frame, we always have to tag it with the parameter t in the Newtonian mechanics to indicate that this is the coordinate of the particle at time t. Okay, now, the radius of this particle, this can be indicated as r, okay, where the x y are the coordinates of this particle. So, this is all about 2 dimensions. In 2 dimension, okay, while the same thing if we have to write in the 3 dimension, then another coordinate z has to appear. Okay. So, in 2 dimension, we can write r as x, say along this direction, let us say E 1 is the unit vector and along this direction E 2 is the unit vector. So, x E 1 cap plus y E 2 cap, this will be the coordinate of this particle written in vectorial terms. So, this is a vector. So, for a vector, the magnitude, it is defined by magnitude and direction. So, this vector once we have written in this form, automatically this includes the magnitude also. So, we can write r magnitude as x square plus y square under root, while this angle which defines the direction, which we can write as theta. So, tan theta can be written as y by x. So, a vector contains both the directions and the magnitude. Now, another important part that we have to deal with in the Newtonian mechanics also we call this as the non-relativistic mechanics. The inertial and the non-inertial frame. So, we will define inertial frame as a non-accelerating frame, and it may be translating, with constant velocity, okay, or may be stationary. While non-inertial frame, these are the accelerating frames. So, we know that the Newton's law, they are applicable in inertial frames. Is applicable here. So, let us start with the kinematics of a particle. So, we are trying to find out the velocity of a particle in 3D. So, let us say this is a trajectory along which some particle is moving. This is our particle at time t. Okay. So, the radius vector of this particle from this point I can show as r. Okay. So, this is our r t, and another point we are taking. So, its radius vector can be defined as r t plus d t, and let us say this is r 1 and okay. To distinguish it, we can write as r 1 equal to r t and r 2 is equal to r t plus d t. Okay. So, we can do a shortcut notation for this. Using a shortcut notation, we can work out which will involve just the with a summation sign instead of writing all the terms. Okay. So, if we follow that notation, then we can write r as x I times E I summation, where x I this refers to for I equal to 1 to 3, and we can write here x 1 equal to x, x 2 is equal to y, and x 3 equal to z. And similarly, we will have the E 1, this is equivalent to here unit vector in the direction of x, E 2 is equivalent to unit vector in the direction of y, and E 3 cap this is equivalent to unit vector in the direction of z. So, these are unit vectors, and these are also unit vectors. So, we can put here these are identical. So, the velocity of as the particle is moving along the trajectory from this point to this point. So, this quantity let us make another figure. The second axis we can show here, and say the trajectory is looking like this. So, this is your delta r, and here we can write it as r t, and this becomes r t plus delta t. Okay. So, delta r we can write as r t plus delta t minus r t, and therefore, r t by delta t okay. Now, the velocity vector, this is defined as the velocity at time t, this can be defined as limit t tends to delta t tends to 0, delta r by delta t, this we can write as limit delta t tends to 0, r t plus delta t minus r t divided by delta t. Okay. So, this V t will get reduced to then limit delta t tends to 0. Now, r t we have written as summation of x I, and in the bracket we can write here t to indicate this is a function of t, okay, and together with the unit vector in the ith direction. So, this is the ith component of the radius vector. So, this is the radius vector which is r is composed of x 1 E 1 cap plus x 2 E 2 cap plus x 3 E 3 cap, okay, and here we are putting t to indicate that this is at time t. So, with x 1, x 2 and x 3 also the time tag will come, which we have not shown here, and these are the components of this radius vector along the E 1, E 2 and E 3 directions. Okay. Similarly, we can write here the r t plus delta t as x I t plus delta t, and the summation, and summation is obviously for I is equal to 1 to 3 divided by delta t, and here we put also E I cap. So, therefore, this can be written as summation can be taken outside, and we can write limit delta t tends to 0, and this will be. So, if we subtract x I minus x I t plus delta t minus x I t. So, we can write this as delta x I t times E I cap divided by delta t, and then summation is over obviously I is equal to 1 to 3. Okay, now, you can see from this place that V then becomes equal to I is equal to 1 to 3, and as the limit delta t tends to 0, we can write this as dx t by dt and C I cap, and this often we write as here I is there. So, x I dot, okay. This is the derivative d by dt x, this is written as x dot. Okay. So, in this simple notation, what does it say, that V t this becomes equal to x dot x cap plus y dot y cap plus z dot z cap, or either you write the same thing as x 1 dot E 1 cap plus x 2 dot E 2 cap plus x 3 dot E 3 cap. Okay. Magnitude of the velocity vector, which we write as V, this will be nothing but the dot product of V dot V under root. So, we can take the dot product now, E 1 cap plus x 2 dot E 2 cap x 3 dot E 3 cap. Okay, and this gets reduced to x 1 dot square x 2 dot square plus x 3 dot square, and take the under root of this, take the under root of this. So, this gives you the magnitude of the velocity, and often we call this as the speed. Now, similarly, we can define acceleration. Okay. To conclude this we can write this V as, instead of writing in terms of x 1 dot, we can also write in terms of V 1 E1 cap plus V2 E2 cap plus V3 E3 cap, okay, where V1 equal to is identical to x1 dot, V2 is identical to x2 dot, and V3 is identical to x3 dot. Okay. Or if you are writing in terms of x, so this you can write as V x times E x cap, this is the unit vector in x direction, V y times y cap, and V z times z cap. Actually, this E1, E2 and E3 cap what I am writing here, this is a more generalized notation for representing a vector, while x cap, y cap and z cap it is a little restricted in sense. So, even for a curvilinear coordinate we can proceed with the E1, E2 and E3 cap, while x 1, y and z it is mostly restricted to the Cartesian coordinates. Okay, now, acceleration is defined as this is defined as the rate of change of velocity. So, proceeding in the same way, okay, so dV by dt, using the equation what we have written here, we can write as V 1 dot E 1 cap plus V 2 dot E 2 cap plus V 3 dot E 3 cap, where V 1 dot is nothing but dV 1 by dt, and then this becomes equal to, if we write V 1 equal to dx 1 by dt. So, this becomes equal to d square x 1 by dt square, and similarly other follows. Okay. And a common notation for acceleration is a small a. So, we can write a small a, this as or this is the component wise we can write a 1 times E 1 cap, a 2 times E 2 cap, a 3 times E 3 cap, where a 1, a 2 and a 3 these are the components of the acceleration along the E 1, E 2 and E 3 directions. Now, the locus of the particle as it moves through space, okay, is called trajectory. So, quite often we are interested in writing the velocity in terms of the trajectory variables, like what do I mean, that if I represent this trajectory here, say this is the r vector. So, we will see later on that the velocity of the particle, this will be given by a tangent vector. So, this is your velocity of the particle and this will be tangent to the trajectory. This is the trajectory which the particle is traversing. So, at this point the velocity is given, velocity will be along the tangent to the trajectory. Now, this velocity can be broken in two parts. Okay, so, I can break it into this part, and this I can write as say the v theta, and another one I can break it along this direction, and this I can write as V r. So, for sorry. So, V can be written as V r times r cap, where r is the unit vector in the r direction, and plus V theta times theta cap, where theta cap is the, or here we can use the same notation as E, indicating here E r, and here also the E theta to indicate this is the unit vector in this direction. So, E theta is unit vector here, and E r is the unit vector in this direction. Okay. So, if we try to represent in this term, so this kind where theta is this angle. Okay. So, this kind of representation is called the polar notation. And it is easy to work out, as we can see that if I write dr by dt, say we start with r equal to r times E r cap. So, if I differentiate this with respect to time, okay, so this can be written as r dot times E r cap plus r times E r cap dot. Okay. So, this is what I indicated here, this is your V r is nothing but r dot, okay, and this part we need to evaluate. So, this will be using frequently in our discussion later on. So, if this is a E r vector, okay, and if we turn it by d theta, and let us say this is at time t and this is at time t plus dt. So, this is the unit vector. So, the change will be delta E r, okay, and delta E r we can write as E r t plus delta t minus E r t. Okay, and from here we can see that this delta E r is nothing but the magnitude of this E r. So, magnitude of the E r cap, we have written E r cap for unit vector. So, E r cap t times this angle d phi, or here we write it as delta theta. So, delta E r. So, now we are writing that this is the magnitude of the unit vector. So, this becomes 1. So, delta E r magnitude wise, okay, so here we will write delta E r. This is the vector, and here we are writing the magnitude wise. So, we are just taking the magnitude of this. So, delta E r becomes delta theta, and therefore, delta E r by delta t, this becomes delta theta by delta t, and in the limit delta t tends to 0, this becomes theta dot. So, what we get that d E r by d t, this is nothing but theta dot, but this is magnitude y. What about the direction? So, direction we can see here. So, for writing delta E r by delta t, okay, we can follow the example here. So, as delta theta, this we if we write as the delta theta angle. So, as delta theta becomes small and small, you will see that this vector will be just perpendicular to the E r vector. Okay. So, therefore, this is directed along the E theta direction. Okay. Limit delta t tends to 0, you can write as E cap theta. So, supplementing here in this place, we can write r dot E r cap plus r times theta dot E theta cap, okay, and this is your V theta, which is nothing but r times theta dot. So, this is all about the polar coordinate. Sorry. So, whatever the derivation we have done right now, this will be very useful the way we have represented the derivative of a unit vector and the derivations we do later on. So, these are representing the unit vectors in the direction E 1, E 2 and E 3. R is the vector at time t, this is at t plus dt or delta t. So, the vector from here to here, this is your delta r t, we can write as delta r t. So, we are trying to represent this in different terms. So, you can see that the black curve which is seeing, this black curve we will write as d s, this segment from here to here. Okay, let us say this point is a sorry, this point is b. So, the black segment and the green segment they differ in length little bit, but as delta t becomes smaller and smaller, that is b approaches a. Okay, if you reduce the delta t towards 0, so it will be closing to a. So, as it closes to a, so dr magnitude it becomes equal to delta s, okay, in the limit delta t tends to 0, in the limit delta t tends to 0, these are equal. Okay, so, this is magnitude wise what we are writing here. Now, dr by dt we can write as limit delta t tends to 0 delta r by delta t. Okay, so, this can be written as limit delta t tends to 0 delta r by delta s times delta s by delta t. Okay, so, already we have seen that from here that as the limit delta t tends to 0, the magnitude of delta r and delta s it is becoming same, and from here we can also see that as delta r becomes closer to 0 means the b approaching a. So, this vector delta r vector this will be just tangential to the tangential at point A. So, as delta t tends to 0, delta r becomes tangential to the point to the curve at point A. Okay, therefore, delta r can be written as delta r by delta s times delta s by delta t in the limit delta t tends to 0, this can be written as the magnitude of this, obviously it becomes 1, and the unit vector tangential to the curve at that point and times this quantity will become d s by d t. Okay. So, what we are getting v, now we can write as d s by d t times C t. Now, referring back to the representation that we gave in this place. So, we can see that we have written in this way here. So, E t, this is a vector which is tangential to this point. So, here what it is doing exactly, once we are showing here as E t. So, E t is nothing but in the direction of this v direction that we have shown, and this can be composed of. So, from here also you can get the unit vector in the direction of t. So, if you try to write from this place, okay. So, this you can write as v divided by v. So, this will give the unit vector in the direction of t. So, this will be v r e r cap plus v theta e theta cap divided by v, okay, because this is the magnitude. So, in this direction this is the E t vector, and v r is obviously we have written as r dot. So, this is r dot by v e r cap, and v theta we have written as r times theta dot. So, this is divided by v e theta cap. So, this is your E t vector. So, we can see that the same thing can be represented in various ways, and they have their own significance as far as these representations are concerned. Sometimes we use the representation in the polar notation where it is convenient, and wherever the this just now we have derived in terms of d s by d t, wherever this notation is convenient, we will be using this. Okay. Now, the next step will be to find out the acceleration. Okay, this we have done earlier. Okay, now, A we can write as d by dt sorry. Okay, so, this is the one way of working out the acceleration. Also we can do this in the polar notation. So, if we take the derivative here, this becomes d square s by d t square times E t cap plus d s by d t times E t cap d by d t E t cap. Okay, this is clear. This factor we need to work out. Okay, this is the r vector at time t, and this is the r vector at time t plus delta t, and the tangent to this we are showing as this is the tangent vector at time E t, and here this is the tangent vector at time E t plus delta t. And if we draw this quantity we have already written as ds, and let us say this is the radius vector r, this also called the radius of curvature, not radius vector, this is the radius of curvature r, and this angle we write as delta phi. So, by the time here this vector, here this is the center of the curvature, this is center of curvature. So, as this shape here this is the Et vector. So, perpendicular to this we have drawn this vector, this is perpendicular to this 90 degree, and as it rotates from here to here, okay, again we are showing this is the angle 90 degree. So, rotation from here to here, this is the ds, and this is a very small segment, and we can write here delta s instead of ds. Okay, so, therefore, your unit vector also it will rotate by the angle this delta phi. So, delta s by r, this is nothing but the angle delta phi, and this is the angle by which your tangent vector will rotate. So, this angle is here delta phi. If we extend it back from this place to this place, so this angle will be represented by angle delta phi. Okay, so, the plane that it constitutes, this small segment delta s and these two radius of curvature lines, okay, it is a called a osculating plane. This constitutes one plane, and this is basically constituted by your E t vector and E t plus delta t vector. So, these are the two vectors lying in this plane, which we call as the osculating plane. Okay. And because this is perpendicular to this and this is also perpendicular to this. So, therefore, your the center of curvature, this also lies in the osculating plane. So, now from here we can work out what will be the d t by what we were looking for, this quantity d t cap by d t. So, I have E t cap, already we have earlier worked as, this can be written as d r by d s. Okay, so, this implies d E t cap by d t, this we have worked earlier just few pages back. Okay, so, d E t by d t we can write as d E t cap by d s times d s by d t. This quantity is nothing but V. Now, this needs to be further evaluated. D t cap by d s, this we can write as limit delta s tends to 0, delta E t cap divided by delta s. And as earlier we have done, this is your E t cap and this is your E t plus delta t cap, and this is delta E t cap, and this angle is your, as shown here in this figure, this is the delta phi angle. Okay. So, therefore, delta E t cap, this can be written as delta phi times this delta E t cap magnitude we will write. This magnitude is equal to 1. So, this becomes delta phi. And you can see from this place what will be its direction. This direction will be perpendicular to the, as delta phi becomes smaller and smaller. Okay. So, this quantity will also reduce, and as this point, this is B suppose, and this is A, as this approaches here in this point. Okay. But here we will write as B prime and A prime to distinguish from any earlier notation. So, as this point approaches here, delta phi becomes smaller and smaller, and this delta E t vector, this will become perpendicular to the E t vector, and perpendicular to this E t vector, let us write this as E n, okay, E n cap. So, E n cap is a vector which is perpendicular to E t cap. Okay, this is the perpendicular notation. So, E n cap is perpendicular to the E t cap. So, therefore, d E t cap by d E t, this can be written as V times d E t cap by d s, which is V times limit delta s tends to 0, delta E t cap by delta s, and this reduces to delta phi by delta s times E n cap, okay, delta limit s tends to 0. And now, delta phi we know from this place, this is nothing but delta s by r. So, we insert here V is equal to limit delta s tends to 0, and delta phi is nothing but delta s by r. So, this is delta s. So, this becomes V by r times E n cap. And now, putting back into our original equation for A, now here we need to insert this, and where V is nothing but V equal to d s by d t, okay, in this place. Therefore, we can write A equal to d square s by d t square E t cap plus d s by d t times d s by d t times E n cap. Now, E n cap, as you can see here, E n cap, as this point, this is point B and this is point A. So, as the point B is approaching A, so the plane which it will be defining, this will be an instantaneous plane. Okay. This is an, as delta t tends to 0, the osculating plane, this is basically an instantaneous plane. Okay. At every instant this plane is changing, and simultaneously the center of curvature will also be changing, and the radius of curvature also this will be changing. So, as this point is approaching here, and E n vector what we are writing here. So, this is approaching here in this place, and the perpendicular to the E t vector, just now we have defined that this is approaching here, and therefore, delta phi is becoming a smaller and a smaller, and the change in the vector if E t plus delta t minus E t, it becomes perpendicular to this vector. So, perpendicular to this vector, it is a where is its a direction, we can see from this place, this is the direction, okay. It is along this direction perpendicular to this vector. So, perpendicular to this vector at point A, it points in this direction. So, in this direction is your E n, write it by E n cap, okay. Its direction is along the center of curvature. Okay. So, thus we have completed here. Now, we can see that this is the E t vector and this is the E n vector. So, your acceleration, total acceleration of the particle, it is composed of two components, d s by t square s by d t square, which is written in terms of trajectory length, and then also d s by d t, this is the d s by d t, this trajectory velocity, also you call as this as the speed. Okay. So, d s by d t and E t n cap, which is along this direction. So, this term also we call as the tangential acceleration, and this is the normal acceleration. And the product of the vector, now you can see from here the product of the vector, if we take a product of this E n cross E t. So, it will be perpendicular, a vector will be which is perpendicular to this plane, this is called the binormal vector. So, E n cap cross E t, this we can represent as E b, and this will be called the binormal vector, and this is also a unit vector. So, this is your tangential vector, tangential unit vector, and this is your normal unit vector, and this is also called the principal normal direction. And while the perpendicular to this will be called E n cross E n cross E t, this will be called the binormal direction. Now, once we have done this, here we are missing one term, E n 1 by r is missing in this. So, we introduce 1 by r here, moreover this is d s by d t times 1 by r. Okay. So, here we will have a term 1 by r times d s by d t square. Okay. After finishing this, later on we can utilize while solving various spacecraft problems. In aircraft, this is this constitutes a very important equation while doing the finding out the equation of motion for the aircraft. Now, next what we are will be working out, it will be quite important from the point of view of our attitude dynamics. Consider a rigid body and in which we have a particle here whose position vector is rho, and this is the particle p. And suppose E 1, E 2, E 3, this is the body reference frame. Located at center of mass. Okay, this is located at the center of mass here and fixed to the body. So, this is fixed to the body and this body is rotating at an angular rate of omega. Okay, so, what I will try to do here, instead of writing A, let us in the beginning will indicate this vector as instead of indicating as a rho, we indicate this by A. So, this A vector, this will have components in the body reference frame okay, where A 1, A 2 and A 3 are the components along the E 1, E 2 and E 3 direction in the body reference frame. So, if somebody is sitting in the this reference frame or attached to this body and the person is also fixed. So, he will see that these magnitudes are fixed. Okay. If this point is fixed, okay, it is a rigid body, means this point obviously it will not move. So, this quantity will remain fixed and these are basically scalars. An important property of scalars are they are independent of the reference frame. Okay, just like take the case of a temperature. So, temperature if you the temperature of a body in a moving train, it will be same as at the temperature of a body if you from a non-moving position. So, that body temperature will automatically it will not change. Okay, a train is moving in which I have kept this pin and the temperature of the pin whatever it is there, it is a scalar reality, it will not change. Okay, similarly, if you look at the top of your ceiling fan and if you are looking from the below, you will see that the length of the blades, okay, it remains same in this reference frame in the our inertial reference frame in which we are sitting, say on this table I am chair I am sitting and looking at the fan on the top. So, this length will not change and also to a person who is sitting on the fan and the fan is moving now. So, it is just like a fan is like a rigid body and it is a moving. So, for that person also the length will not change with time. So, the scalars they do not change with time. Okay. So, basically they do not sorry the scalars they do not depend on the reference frame, rather they may vary with the time if they are variable, but it is not that it is dependent on the reference frame. So, the length of the fan blade whatever it is a person will look from there or the same length I will see from this place. Now, using this concept we will be developing that if there is a vector A and this is a rotating reference frame and I am sitting here in this place, then how the change of this vector with respect to time will appear from the inertial reference frame, which here we write as E 1, E 2, E 3. This is an inertial reference frame and this is a non-inertial reference frame. Okay. So, how the change of this vector will appear from this from the inertial reference frame. So, this can be correlated to the as we will see in the next class E 1, E 2, E 3 we can write as this can be written as in this way. So, basically it gives a correlation, this equation gives a correlation between the rate of change of this vector A as from the E1, E2 and E3 reference frame. So, if it is fixed here, if this point is fixed, so obviously the rate of change of A in the body reference frame, which we are writing as E1, E2, E3, okay, because it is a fixed. So, this will not change here. Okay. So, this quantity will become 0, and therefore, the components of this vector, as you see from the inertial reference frame, the components of this vector along this direction, this direction, this direction, it will be given by omega cross A. So, write in terms of the is a break it up, and that will provide you the components along this direction, this direction. Okay. While in this reference frame, in the body reference frame, you will see that the components will be different. Okay. Here it depends on how it is oriented with the body. So, depending on the orientation with the body, its a component will be defined here, but this component will also remain fixed here in this place. The irrespective of the components either in this frame or either in this frame, the one reality is that the magnitude of this vector, which is the length of this vector from this place to this place, whatever it remains in the rotating reference frame, the same it will remain from the non-rotating reference frame. And this is the crux of this conclusion that we are going to work out in the next lecture. So, we stop here. Thank you very much.